So, this week we have been discussing circuits, right. So, till now what we have completed is resistor and different combination of resistor, what we need to do when resistors are connected in series, when conducting wire is there, what to do when we have Wheatstone bridge, and then we finally reach to circuit symmetry. Okay. So, till now we have reached to circuit symmetry. Let us see one example. Look at this circuit. If I want to find out equivalent resistance between A and B, so I can see input output symmetry here itself. From B directly current will go to A, and then B, across B, two resistors 2 ohm 2 ohm connected, and if I look at A, 2 ohm here and 2 ohm here. So, this circuit has got input output symmetry. You can solve this problem by input output symmetry, but the problem is what current goes here will be delivered by this one, and as you go from this one to this one, there are two junctions involved. If there is only one junction involved, we can comfortably say that current won't get divided, because this current has to be equal to this current. But if two junctions are there, it is difficult to say. So, what we can do, we can think in different way. So, if I can convert this circuit into 3-dimensional circuit, let us see whether we are getting any other type of symmetry or not. So, input output is there, but I am little reluctant of saying that there is no current division here and here. Okay. So, I just want to check it by other way. So, if you take out this inner triangle out, this will become something like prism. Okay. So, something like this you are going to get. All the wires are representing resistance of the given value. If I look at this circuit between A and B, I can see a plane of symmetry, the plane passing through AB and cutting this prism equally this way. So, I can see this as plane of symmetry. So, if this is the plane of symmetry, the point this side of plane of symmetry and the point on other side of plane of symmetry, they will have equal potential. Similarly, this point will have same potential as that of this one. So, if this one and this one, they are at the same potential, then there is no flow of current through this resistor. Similarly, if these two are at the same potential, then there won't be any current through this resistor also. So, as there is no flow of current through this and there is no current flow through this, I can remove these two. So, this one and this one I can remove because there is no flow of current. So, now I am removing this and removing this. Now, look at the structure. This one is given 2 ohm, 1 ohm, and then again this is 2 ohm. Similarly, this is 2 ohm, this one is 2 ohm, this is 1 ohm, and this is 1 ohm, right. Now, if you look at this branch here, if I draw, I am talking about this one. Look at this branch. the current will now follow this path. There is no flow of current through this and this. Similarly, here current will be following this path. These three I can see in series. So 2 plus 1 plus 2 will give you 5 ohm. So this will be 5 ohm, right? And similarly this will be 5 ohm. So what I can see between A and B, this as 5 ohm, this branch as 5 ohm, and the resistor which is directly connected across AB is of 1 ohm. So 5 ohm that will be giving you 5 by 2. So 5 by 2 and this 1, they are in parallel. 5 by 2 into 1 divided by 5 by 2 plus 1. Okay, this is RAB, and we are getting 5 by 7. Okay. So here what we have done, when circuit was in 2 dimension, we were unable to figure out what type of symmetry it had. Okay, even if you are able to figure out what type of symmetry it is having, then we were not getting any direct benefit. So what we did, we converted into 3 dimension, and from 3 dimension we are easily able to solve, and we got this answer. So sometime converting circuit from 2 dimension to 3 dimension will help, or 3 dimension to 2 dimension will also help. Okay, we will see that type of question later. Let us see another example. So here I have taken 3 dimensional structure, bipyramid, and you are asked to find out equivalent resistance between AC and DE. AC and DE. So let us first see AC. Okay, AC means here and here across these two. So as you can see, there is input output symmetry. So whatever the current given to this one, that will be given back by this one. Whatever current given to this one will be given by this one. Whatever current flowing through this one, same will be current flowing through this one. And look at this back resistor which is connecting A and C. So this resistor which is back of the diagram, this will take current directly from A to C. Okay. So as between input and output there is only one junction, I can safely say that there is no flow of current here. Similarly here also there is no flow of current, so I can remove these two. So the resistor connected between DB and resistor connected between BE, they are not carrying current. Okay. So I can remove these. Now here 2R, this one 2R, this one 2R, and the back one R. So this 2R, this 2R and this 2R, they are connected in parallel, 2R by 3. Okay. So these 3 branches I have directly added, A and C, we have 2R by 3. Okay. And this, the back one which is directly connecting A to C, is R. Now they are connected in parallel, I can write 2R by 3 into R divided by 2R by 3 plus R. So what we are getting is 2 by 5, 2R by 5. R equivalent across AC, 2R by 5. Okay. Now second one, DE, DE. Okay. So I will write it over here first. Let us clear all. So we got 2R by 5 I feel, right. This is R AC. Okay. Now DE. So across DE we have to see again we are getting input output symmetry. Look at the circuit. This current will directly go and reach here, this current will reach here, and this current will reach here. Okay. So there is no role of this and no role of this resistor. I hope it is clear. Now DE, this is this one. Separately I can draw 2R and so this particular branch I am drawing separately. Now this branch and this branch, here what is happening, this R and there is this one R, again R, something like this I can draw. This branch R, this branch R, and this R, they are connected by a single R. Here you can see Wheatstone bridge, this one upon this one is equal to this one upon this one. So as the ratio here and ratio here matching, this is of no use. So I can remove this resistor, and now I can see 2R, 2R and 2R, they all are connected in parallel, 2R by 3. So RDE is 2R by 3, right? So first answer is 2R by 5 and second answer is 2R by 3. So 3-dimensional structure, we are able to see input output symmetry, we use the concept and we are able to solve it. Okay, let us move to next example. Again I have taken one 3-dimensional structure. What is the equivalent resistance of this across AB? Okay, between AB we need to find out first. And all the wires are having resistance small r. Okay. Now look at AB. You can pass a plane through AB about which the circuit is symmetric. If I take midpoint of FD and I take midpoint of EC, okay, now I can see that I can pass a plane I hope you can visualize. So passing through AB, there is a plane which is cutting this whole thing into two equal halves, point D and point F. Point D is this side of the plane and point F is on other side of the plane. So potential here and potential here same. Similarly potential here and potential here same. Now I can draw diagram in a simplified form. I need resistance between AB. Okay. So resistance between AB, A, B and FD will be somewhere here, F comma D, and similarly EC. This way I can draw diagram. I already told you the procedure. Now connect the resistors here and simplify, you will get answer. Okay. If you look at the circuit, directly you can tell answer. So instead of drawing points and all, I can directly tell that as D and F, they are at the same potential. Look at this D and F, they are at the same potential, and this E and C, they are at the same potential. There is no flow of current through this resistor. There is no flow of current through this resistor. Similarly, there is no flow of current through this resistor. This I can remove. So what I can see is AD, this one, and then I will get this diagram. I have removed FD resistor and EC resistor. This is the diagram I am getting. All are of resistance R. If all are of resistance R, this is R, they are connected in series. This is 3R. Similarly 3R, and this is R. So 3R, this one is 3R, and then the one which is directly connecting AB is R. Three R by 2 into R divided by 3R by 2 plus R. So 3R and 3R will give you 3R by 2 parallel combination. Then I am connecting in parallel with R. So what I can see, 3R by 5. So this part you are going to get 3R by 5. I hope first part is clear. Let us see another part. AB over, if I ask AF, so I am adding one more question between A and F. So I will erase all. AF. Across AF it is little difficult to decide. So what we can do, we can convert this 3D into 2-dimensional diagram. Otherwise you can directly see that there is input output symmetry. Okay, input output symmetry. So what I will do, I will stress the front one and place it over back one. So this front one I am stretching, this triangle I am stretching. So here this is A, F, D, okay, and then I stretch it and press it on the inner one. So inner one will become something like this. So A is connected to B, B I will draw here, and then F is connected to E, F is connected to E, and C is connected to D. Okay, so one resistor I can see here, another resistor here, one more resistor here. Now this has become very simple, and from here we can easily decide. If I look at the flow of current, this current will directly flow A and F, A and F. This current will directly flow, and between input and output we have only one junction. So this current will directly flow, no problem. If this current is directly flowing, there is no division of current here. I can remove this resistor. If I remove this resistor, this is what we are getting. Upper one 2R, this is 2R and R, 2R and R, 2R by 3. So 2R by 3 plus R, 5R by 3, 5R by 3 plus R, 5R by 3 plus R, 8R by 3. So this whole thing will be 8R by 3, okay, and this upper one is 2R, and this direct one is R. This I need to add. So what I can write, 1 upon 2R, all are connected in parallel, then 1 upon 8R by 8R by 3 plus 1 upon R is 1 upon R equivalent. So now you can simplify, multiply and divide by 4 here, 4, and multiply and divide by 8. So 12 plus 3, 15, 15 by 8R, that means 8R by 15 is equal to R equivalent. This is the answer, right? So this we converted 3D into 2D. Previous example we converted 2D into 3D, reverse process. So sometime converting 3D into 2D you can easily analyze, and in some cases converting 2D into 3D you can easily analyze. So you have to think in all the direction to simplify the circuit. Okay, I hope this concept is clear. Now let's move to next one. Cube. So all the resistors are connected across the edge of a cube, and you are asked to find out equivalent resistance between 1 and 4 and 1 and 3, 1 and 4. Look at this one, 1 and 4. So across 1 and 4, I can see if you make a plane pass through 1 and 4, it can divide the whole circuit into 2 halves. If this is the way we have the plane, joining two diagonally opposite ends, right, two diagonally opposite edges. So above and below we have got similar circuit. If that is there, then I can say that potential at 3 potential at 3 and 8 will be same. Look at the diagram carefully, 3 and 8 it will be same, and then between 2 and 5 also it will be same, 2 and 5 it will be same. So if we want to simplify the circuit, we can draw these two as one point and these two as one point, right? So drawing 2 and 5 as one point and 3 and 8 as one point, I can redraw the circuit. Let's see how we are getting. So 2 and 5 single point, 3 and 8 single point. We want to find out resistance across 1 and 4. So let's start connecting resistor between 1 and 5 and 1 and 2, these two resistors. So they are connected here. Similarly between 4 and 3 and 4 and 8, 4 and 3 this resistor and 4 and 8 this resistor, they are connected here. Between 1 and 4 there is one direct resistor, this resistor I have connected here. I hope up to this point there is no doubt. And the remaining 2, 5 and 3, 8, 2, 5 and 3, 8, between 2, 5 and 3, 8. So between 2 and 3, 1, and 5 and 8, one resistor. So 2 resistors I have connected here. Similarly the remaining resistor you can place, you are going to get this diagram. Okay, now here this is R by 2, this is R by 2, R by 2, R by 2 will make it R, that R will make it 2R. So this is 2R. And this will be R by 2, that is here, R by 2. This is R by 2, here it is connected R by 2, this R by 2 is connected here, and then this R by 2 is connected here. Now we start seeing all series parallel combination, and here this 2R and 2R by 2R and R by 2, they are connected in parallel. So what I can draw here for this part, 2R by 5 parallel combination, and this R by 2, and this R by 2, R by 2. So adding this will give me R plus 2R by 5, 7R by 5. So this will be 7R by 5, and then it is connected in parallel with this R. Okay, if you simplify this one, then you are going to get 7R by 12, right. So circuit was in 3 dimension. As circuit was in 3 dimension, I got plane of symmetry. After getting plane of symmetry, I can easily decide which 2 points will have same potential. 2 points having same potential can be drawn by single points like this, and this way we can simplify the circuit. Okay. Now let us see next example. Between 1 and 3, look at this 1 and 3. Can you pass a plane across 1, 3 about which circuit can be symmetric? So visualize that if I pass the plane this way, okay, so 5, 7, 5 to 7, little tilted diagram I will draw, otherwise everything won't come in the proper way. So I am drawing this way, this is connecting to 7 and this is connecting to 3, and then I hope you are able to understand. Let us do one thing. Now I can easily draw plane. Okay, I have changed the diagram. I am talking about the plane passing through face diagonal. Okay, plane passing through face diagonal, join these two and then join this and this. Now it is coming properly. Look at this plane. Now I hope you can see clearly, okay, and if this is the plane about which circuit is symmetric, above this point and below this point, they must be at the same potential. This one and this one, they will be at same potential. Similarly above this point and below this point, they will be at same potential. Okay, so this 2 and 4 I can draw as one point, and similarly 6 and 8 I can draw as one point. So let us see. So we understood the diagram. Okay, I will erase. Two and 4 same potential, 6 and 8 same potential. So 2 and 4 single point, 6 and 8 single point, and you are interested in finding resistance between 1 and 3. So 1 I have drawn here, 3 I have drawn here. Start connecting resistors between 1, 2 and 1, 4. Between 1, 2 and 1, 4, 2 resistors I can see that I have connected here, and then between 3, 2 and 3, 4, 3, 2, 3, 2 and 3, 4, 2 resistors, these two here. Okay, this way if I connect all 12 resistor, I will get something like this. This I need to simplify. R by 2 and R, 3R by 2. Okay, so joining these two or combining these two, 3R by 2. Similarly below one, R by 2 and R, 3R by 2. This is over. This is R by 2, this is R by 2, R by 2, R by 2. and then the one which is directly connecting 6,8 to 2,4. 6,8 to 2,4, there is single resistor of resistance R by 2. Now across A3, 1 and 3, if you want to find out, we can see Wheatstone bridge, this one upon this one is equal to this one upon this one. The ratio here is same as ratio here. If the ratio here and same as ratio here, there won't be any flow of current through this resistor. I can remove, okay. If I can remove this one, then I will get this structure. After removing the middle one, 3R and R, 3R and R, parallel combination, 3R into R upon 3R plus R, 3R by 4. So this will have resistance 3R by 4, okay. So using plane of symmetry, I am able to decide which 2 points are at the same potential and I can solve it. Here you can see input output symmetry as well. So input output symmetry, if I go by, okay, let us do one thing. In another slide I will solve it. So if I want to find out 1 and 3, okay, so here I will make it 3, 1 and 3. Previous one I want to solve by input output symmetry. So front one, if you stretch and press it over the back one, the whole diagram will come in 2 dimensions. Let us draw the diagram. 1 and 3, say this one 4 and this one 2, and I am pressing over this one. 1 is connected to 5, so I can visualize it this way, 5, and then 4 is connected to 8, this is 8, 3 is connected to 7, this is 7, 2 is connected to 6, and 2 is connected to 6. There is one resistor here, one resistor here, one resistor here, and one resistor here. Okay, across these 2 terminals, I want to find out equivalent resistance. Okay, so now there is input output symmetry, and only one junction involved between input and output. So this current will directly flow, this current will directly flow. These 2 resistors are of no use, I can remove. So this I can remove and this one I can remove. This is what we are getting. So 2R and 2R parallel combination will give you R. So this whole thing is R, R, R. So this inner one is of 3R. So inner one of 3R, this upper one 2R, and this below one, that is again 2R. This 2R will make it R. R and 3R parallel. That means R into 3R divided by R plus 3R will give you 3R by 4. This is R equivalent. Right. So if you look at the previous one, this is method 1, plane of symmetry or folding symmetry we solved, and then this is method 2, input output symmetry. Okay, both the cases we are getting 3R by 4, 3R by 4. So as you can see that this is taking lesser time because we are easily able to decide which one is to be removed, and after removing series parallel combination we can reduce the circuit, right. Now same question, between 1 and 7 you can see there is line of symmetry. If I join this 1 to 7, okay, diagonal. So diagonal of the cube, if you think about the diagonal of the cube, then you can see line of symmetry, okay. And with respect to that line of symmetry, the point here 2, 3 and 4, they will be all same. Visualize the diagonal of the room and visualize nearby corners, right, with respect to that diagonal. So upper one and that corner one and this corner one, they will be at same potential, okay. Similarly from here, if you see these points, this one and this one, they will be at the same potential. So 2, 3, 4 can be considered as single point, and 6, 5, 8 a single point, okay. And we have to reach from junction 1 to junction 7, across 1 and 7 we want. So from 1 to 2, and I have drawn this one, okay. So this 6 with respect to this one, this branch, this branch, this branch, they will be at same potential, and 2, 4 and this 5, they will be at same potential. So just make a small correction here. So 2, 5, 4, this is 2, 5, 4. Actually I was unable to see the diagram properly. 2, 5, 4, and here this is 6, 3, 8, okay, 6, 3, 8. From 7 there is one resistor here, one resistor here, one resistor here, right. So this one, this one, this one, they all carrying same current into resistor will give you potential difference. This one, this one, this one, they will have the same potential. Similarly from here, if you see one branch and you will reach to 5, one branch you will reach to 4, and one branch you will reach to 2. So 2, 5, 4, okay, now it is correct. Let us connect all the resistors between 1, 2, 1, 5 and 4. There are 3 resistors. Similarly from 7, 6, 3 and 8, there are 3 resistors connected. So out of 12, 6 we have already drawn, remaining 6. So between 2 and 6, 1, then between 3 and 4, 1, okay. So remaining resistors are connected between these two terminals, you can see in diagram. So remaining 6 I am connecting across these two. So these are connected in parallel R by 3, then these are connected in parallel R by 6, these are connected in parallel, that is R by 3, this is R equivalent, and what we are getting 5R by 6. So equivalent resistance across 1, 7 is 5R by 6. So we have seen across 1, 4, 1, 3, 1, 7, okay. So we have calculated across all the combination, all the possible combination, right. So I hope this whole concept is clear. Now there is one more approach I am telling you second method. Across 1 and 7 there is input output symmetry, okay, and no matter whatever path you follow from 1 to reach to 7, all are containing same number of resistor, all path are direct paths are same. So, as all paths are same, if I connect it to V volt battery, I can say if this gives current I, out of that 1/3 current will follow this path, 1/3 current will follow this path, and 1/3 current will follow this path. As it is having input output symmetry, the current which is delivered by this branch, delivered to this branch, this branch, this branch, those will be returned by these branches, I by 3, I by 3 and I by 3, because all are identical. Now, as this I by 3 reaches here, it gets further divided into two equal parts, because both the paths are same. If you look at this path and this path, both the paths are same. I can say this will be I by 6 and this will be I by 6. Now, if you are unable to see series parallel, you are unable to see any conducting wire or Wheatstone bridge or symmetry, so the last option we have, or the simplest one, is the ratio of what voltage you apply to what current circuit takes from the source, that ratio is called R equivalent. So, anyhow if I can find out this ratio, V by I ratio, then I will get R equivalent. If I select a particular branch, or any branch, if I select say this branch to reach to 7, this branch, this voltage will get divided into 3 parts, right. So, this voltage I can write V is equal to current I by 3, potential drop here, current into resistor, first one I have written, current into resistor I by 6 into R, plus current into resistor I by 3 into R. So, this can be written V is equal to 5 I R by 6, and V by I is what? This is 5 R by 6, this we are calling what? R equivalent. So, this is the another approach of solving question. If you can somehow get V by I ratio, then you will get R equivalent. I hope this concept is clear. Now, based on this one, let us take one more example. If I give you this circuit, look at this one, no series parallel, so our first step, direct series parallel. Okay, this first step. Second step, conducting wire. Then we go for Wheatstone bridge. Then we look at the circuit symmetry. So, these are the steps we follow while reducing the circuit. So, here I am not getting series parallel combination, I cannot use this concept. There is no conducting wire connected across two junction, this is also not possible. By with this method we cannot reduce the circuit. There is no Wheatstone bridge. As you look at, this ratio is not equal to this ratio, this is 2 by 4 and this is 4 by 2. So, these ratios are not equal. Okay. Now, circuit symmetry. So, this type of symmetry is called reverse input output symmetry, okay, that we will talk later. But whatever be the symmetry, we are not getting any help from the symmetry. So though this is there, but we are not getting any help. So the last thing what we can do, I will try to get the ratio. If I assume this to be V, later I can substitute the value of 10, value of V as 10. So V divided by I, this whatever I am getting here, that will give me R equivalent. So I was talking about this type of circuit where you cannot reduce the circuit by 4 technique what we have already discussed. So the last technique which we just discussed, that is ratio of potential and current, will give you R equivalent, right. This way you can reduce the circuit. As this particular circuit requires Kirchhoff's law and all, so later we will discuss this. Right now we are not discussing. You can try on your own. So if you are aware of Kirchhoff's law and all, you can try on your own, but after dealing Kirchhoff's law, we will come back to this problem and solve it. Now let us move to next slide. So basic circuit element resistor we have discussed. Today we will discuss voltage source, and later we will talk about switches and all. So in this chapter you will be getting resistor, voltage source and switches, right. So resistor we have already discussed. Now let us talk about voltage source. Any cell, if I take electrolyte cell, then inside electrolyte cell there will be electrolyte and there will be 2 electrodes, right, anode and cathodes. So what happens, this cell delivers current at constant potential difference. So I can say these 2 terminal maintain a constant potential difference when connected to any circuit, okay. So any source, current source, maintains the constant potential difference across its terminal and delivers the current according to the requirement of the circuit. So depending on the resistance of the circuit, different current will be given to the circuit, okay. Now so any source, battery, photovoltaic cell or thermocouples, batteries, generator, photovoltaic cell and thermocouples are the example of such devices, right, which are called sheets of electromagnetic force. Any such device can transfer energy into circuit, and that is why it is called source. So ultimately this is the source which will be connected to passive circuit and it will deliver the current. What this is doing is, it is converting its chemical energy to electrical energy. If you use generator, mechanical energy is converted into electrical energy, right. So energy converter is the better term. Cell is what? It is converting energy, either it might be chemical energy to electrical energy or mechanical energy to electrical energy, right. Now electromotive force, we will define this term, but for time being we are defining one term, that is called electromotive force, is the maximum potential difference between the 2 electrodes of the cell when no current is drawn from the cell. So first definition of EMF across the cell is, it is the maximum value of the potential difference across the cell, but this is not the proper definition. Better definition we will see in the next slide, okay. So any cell that is converting one energy into another energy, in this case electrical energy is getting converted into, chemical energy is getting converted into electrical energy. Now let us see. So inside what is happening, if I want to see, outside movement we already know that when I connect some battery or some resistor over here, then outside there is movement of electron, but inside electrolyte there is a movement of ions, right. So between anode and cathode there will be movement of ions, ion will be moving inside. So as one is positive terminal and another is negative terminal, there exists a conservative electric field. So there is conservative electric field from A to B, okay, and if cell is open state, so when battery is not connected and cell is open, nothing else is connected across two terminals, then ions inside will be in equilibrium. There exists electric field, conservative electric field, but ions are in equilibrium. That means there must exist a non-conservative field in opposite direction. So if cell is open, all the ions are in equilibrium, that means there must exist one more force that is non-conservative in nature, and we can assume that that force is due to non-conservative field, right. So a non-conservative electrostatic field or non-electrostatic field is same as if there were non-electrostatic field En, in addition to purely electrostatic field EE. So there is electrostatic field because it will be positively charged and this will be negative charge, there will be electrostatic field, and as charged particles are not moving, there must be a non-electrostatic field. They must counterbalance each other, then only these ions will be in equilibrium when cell is open, right. I hope this point is clear. Now if source is open, the charges are in equilibrium. If charges are in equilibrium, that means the net field has to be 0 inside. So non-electrostatic field and electrostatic field, they must be balancing each other and charges will be or ions will be in equilibrium, right. Let us move to next one. How we are defining EMF? If you look at previous one, to move ion from one electrode to another electrode, how much this non-electrostatic field is working per unit the charge of ion is defined as EMF. Look at the definition. The work performed by non-electrostatic field per unit charge when a charge moves from B to A, from one anode to another, from one electrode to another electrode. If we are moving charge, then how much work is done by this non-electrostatic field per unit charge is called electromotive force of source. Though we are writing force here, its unit is volt. So unit of electromagnetic force is volt, right. When source is open, EE is equal to minus En, and EE, this one, if I multiply to displacement, then this will become potential difference, and here this we are defining as EMF. So when in open state, this VAB will be equal to EMF, okay. The electromotive force is the maximum potential difference. This is another definition, so this is the better definition, and this is also the way we can define electromotive force. The electromotive force is the maximum potential difference between the two electrodes of the cell. Condition is when no current is drawn from the cell, okay. When we are not taking any current from the cell, that means that cell is not connected to any circuit, then we can say that EMF or electromotive force between two terminal of cell is maximum potential difference or equal to the potential difference, right. Now let us look at this one. So when I connect something across the cell, so this is representing cell, and when we connect cell to something, then current start flowing because two terminals are maintaining potential difference, so current start flowing. So inside that conductor there will be electric field,
okay, conservative in nature, this electric field will be there, and that electric field will be forcing charge particle to go. So electron will be moving opposite to the field this way. Now as here charge particle starts moving, electron will be moving in opposite direction. Inside there will be movements of ion. So ions will be moving through the medium or through the electrolytes. That electrolyte will offer some resistance to the flow, okay. So as electrolyte is offering some resistance to the flow, we will say that cell is having some internal resistance, okay. So cell will have some internal resistance. Under the closed circuit condition, the total electric field inside, this is another point, let us see that. So obviously when you connect it, charge start moving, that means this En must be greater than Ee, this quantity must be greater than this quantity, then only ions start moving. So non-electrostatic field force must be greater than electrostatic field force, then only ion will move from one electrode to another electrode, okay. So under closed circuit condition, the total electric field inside the source cannot be 0, because the net only will start drifting the ions inside, because some net field is required in order to push the charge through the internal resistance. I hope this point is clear. So when you close or when you connect battery to some external circuit, inside this non-electrostatic field will be greater than electrostatic field, and it starts pushing the ion. So if it is start pushing the ion, then this VAB will be less than E. E is what? Work done by this one to move charge from here to here, right. And E, according to this conservative field, we are defining the potential difference. So this has to be more than this, that means EMF must be greater than potential difference if you are drawing current from the battery. So the difference is equal to what is the work done by non-electrostatic force and work done by electrostatic force, that difference must be equal to current into resistance. So whatever resistance this medium is offering to the flow of ions, okay, so the difference will come because of the internal resistance. If we have ideal cell, there is no internal resistance, then work done to move ions from one electrode to another electrode per unit charge will be equal to the potential difference. But if our electrolyte is non-ideal, it will have some internal resistance, the difference will be equal to I into R, okay, current into internal resistance. So we can write VAB is equal to E minus IR. VAB is equal to E minus IR. I hope this point is clear. So this is when we are drawing current from the battery, where R is the internal resistor. So let us talk about some situation, then it will be more clear. So if I have a cell, okay, first thing we have just seen that electrolyte offer some resistance to the flow of ion, okay. So inside there is electrolyte that is offering some resistance to the flow of ions, okay, that we are calling internal resistance. So for ideal cell, internal resistance is 0, okay. But if cell is ideal cell, means we are assuming that the electrolyte inside is not offering any resistance, but that is ideal condition, not the actual condition. Actually all the electrolytes will be offering some resistance. So non-ideal cell, I can say non-ideal cell will have non-zero internal resistance. So when I draw cell in the circuit, this is the symbolic representation, 2 bar, one bigger one, another smaller one, and this is the symbolic representation of ideal cell. If cell is non-ideal, then this is the symbolic representation. So we connect one resistor in series this way, and this is the representation of cell, non-ideal cell. Okay, so this R is internal resistance of the cell. So when it is open, I already told you, when it is open, then I is equal to 0, this current won't be there. This current is 0, I is 0, and the potential difference here will be equal to EMF, first case. Second case, if we are drawing current from the battery, just now we have seen, if we are drawing current from the battery, potential difference will be somewhat less than the EMF, it will be E minus IR, and potential difference is less than EMF. If we charge the battery, right, so if you are discharging battery, that means we have connected some resistor this way. Okay, if I am charging the battery, I might have connected another battery of higher potential difference this way. For example, if I say this is 2 volt and this is 10 volt, so obviously 10 volt will give current and the current flow will be like this. In this situation, the potential difference across the terminal will be E plus IR, right. For time being, just remember this one. In today's class we will talk about this, tomorrow's class we will talk about this, right. So E plus IR, why it is coming, that we will see tomorrow. Just keep in mind that if battery is getting charged, then it is E plus IR. If it is the case of discharging battery, then it is E minus IR, right. One more possibility is there, that is we just connect two terminal of battery by conducting wire. So if I connect these two terminals, then potential difference will become 0, and that means E minus IR must be 0. If I solve this equation, then I will get I is equal to E by R. So you are going to get these cases in circuit, that is why I am discussing all these cases. Battery can be open, battery might be discharging, battery might be charging, or battery might be short circuited, right. So all these cases we will talk about in the next class. So I hope you enjoyed today's class.